Let me introduce the next speaker, Dr. Björn Paulsson from Paulsson Inc. He will present a case for instrumentation for combined natural gas hydrogen storage in Central California. We have to start somewhere, and we start with mixing hydrogen and gas. Take it from here, Dr. Paulsson.
So, and you can see my screen?
Yes.
Okay, perfect. I'll talk about green hydrogen energy for the future. This is a joint presentation by Paulsson Inc., my company, and National Renewable Energy Laboratory in Boulder, Colorado, with Dr. William Butner as head of that program. With me, I have myself and reading her and Dr. Michael Wiley are sort of part of our science team. And we'll focus in on what we do is develop sensors. We have developed fiber optic sensors to safeguard the generation, transportation, and storage of green hydrogen. The outline will start to talk about production of hydrogen from green energy and use as an energy buffer from low to high energy demand. Previous speakers have really laid the ground for that, so I will touch on that very, very quickly. I'll talk about the new CRADA, the Corporate Research and Development Agreement Department of Energy just funded actually in November. So it's a brand new agreement. And we'll talk about underground storage of green hydrogen, which is, I think, has not been touched on previously, but I think will be a very big deal. And we'll talk about fiber optic sensors, as I mentioned, and the underground gas storage market size. I mean, what is the business in this? So the team, our science team, myself, I've been doing this for underground monitoring for over 40 years now. Dr. Reading Her, he's our processing geophysicist, process all our data we record, and Dr. Michael Wiley developing our optical sensor systems. So why interest in hydrogen? Well, we must have an energy storage due to intermittent wind and solar and excess geothermal. I just want to make a plug for geothermal. Geothermal almost never come up in discussion, but it can be a fantastic resource, green and very large if it's done, we put some funding into that. And we are shifting it from the high demand when solar energy is not available, and hydrogen can really meet this demand, can meet this need. And it can be produced 100% green by excess daytime solar, wind, and geothermal, by electrolysis of water. And today, it can be mixed at 20%, am I told, with natural gas, so we can use hydrogen in the existing current infrastructure, and it burns clean, as most of us know. Hydrogen plus oxygen, you get water plus 286 kilojoules per molecule of hydrogen burn, creating as a water and energy. So I just want to touch on this for very, very shortly, because it's been addressed by some of the previous speakers. We're going from wind and solar to hydrogen, and in the meantime, we store it. And I want to make a plug for something called Offshore Wind California. This current administration has just approved 2 very large fields offshore California to develop wind energy. And I think from that wind energy, we have a chance, since it's a project we just started, we have a chance to really engineer that whole system from generation to transportation to storage of that of the electric energy in form of hydrogen in this case. And what's the opportunity? Storage capacity of different solar systems, underground gas storage is very efficient. If you're looking at batteries, and I think it was confirmed by the previous speaker, you're talking about 15 megawatt hours approximately in the low tens of megawatt hours anyway. When you talk about storage of hydrogen and the what do you call substitute natural gas, we're looking at 5 orders of magnitude larger capacity, and it's very long term. Natural gas has been stored for a very long time in 400 fields in the United States today. We'll come back to that a little bit later, but it's a very large capacity, and it is long term. So as I said, DOE funded the Corporate Research and Development Agreement this month. addressing hydrogen manufacturing, transport, and storage. And we are partnered with the two national labs, National Renewable Energy Laboratory and National Technology Laboratory in Pittsburgh, together with GTI and EPRI, which together forms the Low Carbon Resource Initiative. And we are part of that group as a sensor company, providing the sensors for all aspects of this hydrogen process. And this is a slide with too busy, I know, but I wanted to sort of point out where we are. We are in the sensor side of this really complex matrix of hydrogen production, transportation, and storage. It's obviously it's a very complicated system, and that cannot be all those details. You need much more than 20 minutes to go into details on that. But here's a DOE announcement: $8 million for this national laboratory H2 to scale project. And again, we are into the next generation sensor technology, and that's where we fit in. The NREL in Boulder, this is their site. They have wind power already, they have solar power already. They're now using that as a pilot plant to generate the hydrogen, and then we'll transport it in short pipelines, again, to develop that technology. A lot of metallurgic consideration in transporting pure hydrogen, and store it in underground formations. And the way you do this is that you're pumping it down either in porous sandstone, which is typically for most of the gas storage fields in the United States today. There are also salt caverns, mostly in southern United States, Louisiana, Texas, etc. But those are the kind of a sort of pictorial concepts of storing of hydrogen. Today we're storing, as I said, 400 gas fields. One of the biggest was Aliso Canyon, or is Aliso Canyon, because it's still operational just north of Los Angeles. But about 6 years ago, a terrible accident happened. The well blew out, and you can see that we lost 107,000 tons of methane. A total cost for California, Southern California gas as today is $2.8 billion, if I got the numbers right. So obviously, storing is gas safe makes economic sense, makes environmental sense, of course, but it also makes a fundamental economic sense as well. So we are currently active in a place in Northern California, just outside Sacramento, actually just outside Stockton, which has 87 wells, stores 82 billion cubic feet of gas. It's the 8th largest underground gas storage field of 400 in the United States. And we are on this site here with the yellow ring. And you can see some of the operations. This is driving into the field. As you see, that's a very rich agriculture area of California. And that's the most of the rice in the world, I think, is produced in this area. You can see that the storage site is here, again, with 87 wells. And we have installed our first system. You can see some of the wellheads here onto the to the left side, the bottom left on the screen. And there you can see our optical sensor arrays. We installed 2 systems, and UC Berkeley installed one electromechanical or electromagnetic system in one of the systems. You can see that the drilling rig or a small workover rig, and here you can see the 3 Inconel tubes with a fiber optic inside them going into the well. And this well is particular was installed to about 5,200 feet, or about 1,700 meters. There's this after the installation. We have the tube. We out actually last week terminated the fibers, put it into our instrument, and we actually recorded the first gas flow data October 28th this year, just about 2 weeks ago. So this is a brand new installation, and we'll be there for years to come, monitoring this underground gas storage. And this is a pictorial what it looks like when you have the wellheads, you have the casings, you have the underground cavern, either porous sandstone or salt, and in there in the well we're lowering down our or put our fiber optic sensors on tubing. So the 2 sensors we have installed was enhanced distributed acoustic sensor. It's 10 times more sensitive than a regular distributed acoustic sensor and a distributed temperature sensor. Other sensors are our vector sensors, 100 times as sensitive as geophone. We have a borehole source. We have optical pressure sensor arrays. We have other optical sensors as well. And we install that on tubulars. This is a survey we did for Battelle, and I'll show you some of the data from here, which will be a good analog for monitoring natural gas and hydrogen in the subsurface. And we monitored that for 2 weeks, and you should be able to hear actually the flow of the CO2 into the formation as recorded by our optical accelerometers. And these are magnitude -5, so it's a very small magnitude event, but we can actually see the amplitude of these events, and recording the flow of the subsurface gas allows us to track it. And over the month we were there, this is for a curve from Battelle, where they recorded the injection pressure and our microseismic events, about slightly short of 1 million microseismic events over that period of month. We can see even when the small events, they increase the pressure here. 12 hours after that, we got an increase in the microseismic event. On June the 30th, it increased the pressure. 12 hours after that, we started to see an increase in the microseismic. So we also have not only see the events, but we can also track the lags of when something happened when it started to inject. And here's the third event, increase in the pressure. 12 hours after that, we see an increase in the events. And data from real surveys, we're not just doing microseismic monitoring, but we also do imaging. Basically, think of it as some kind of a Earth cardiogram. You can actually monitor where the gas is. And this is from the survey we did a number of years ago for an oil company in Wyoming. We can actually see where the CO2 is going into the Earth and how it's going up dip in the geologic section into the production well. So I very clearly see where the gas is in the subsurface. This is from a surface survey we did for Department of for BP, where we monitored or imaged the natural gas concentration in the largest gas field in the United States. And you can clearly see where you have large gas concentrations. And obviously that's where you want to drill the wells, but it can also be used to monitor where the gas is, the injected gas is in your formation, because if you can control and know where the gas is, you have control where it's leaking, where it is, etc. So it's like having a speedometer on the car. You need to know where it is, how fast it's going, where it's flowing, etc. The size of the market, the underground gas storage, and that does not even include the storage of hydrogen, which I think will accelerate the size of this market. It's a $450 billion market today in the United States, and it's estimated to grow to $760 billion in 5 years by Factors market study. Carbon capture, much smaller. It's probably not even $1 billion today, but expected to be 10 billion in 2027 and go to 200 billion in 2050, according to a couple of market studies. And geothermal, actually my personal favorite of underground energies, is a very small market, but I hope that market will grow, and because it's properly engineered, it's a fantastic opportunity. Called being in California, we are just located just north of Los Angeles. We have tremendous geothermal resources on the east side of the state, and close carbon capture market, close analog to the underground gas storage. They expect that we have to drill 14,000 wells into 2050, 500 wells per year. Just to put that in a perspective, unconventional oil and gas, 2019, before the COVID crisis hit, drilled 20,000 wells a year. So drilling 500 wells is within the industry capability, so no problem at all. So, but it's driven by the net carbon zero goals and a 45Q tax credit, which will largely finance this transition. And I want to acknowledge all the benefits, all the support we have received from from Department of Energy, now also Department of Transportation and California Energy Commission, which have made the development of these sensors and experimenting with them possible. So thank you so much for your attention.
Thank you very much, Dr. Paulsson. You and I started our careers as research on nuclear waste disposal in Sweden in 1978, just shortly after Jurassic. That was a fantastic time.